In this video, I'm just going to recap some of the basics of differentiation. So, differentiation changes something by looking at its change. You have some function f, and you wish to know about its rate of change, and that's what we do when we differentiate. So here, we have a function c and derivative is 0 because c is a constant, so there's no change. The line is x, the derivative of x is 1. Derivative of a times x, a is a constant, is a. A is the rate of change, the dy dx. Squared is 2x, and so forth. And these are the basic rules, but really the thing to remember with differentiation is you're trying to get more information about the function. You're interested in how it changes with respect to something. So all these first functions and all this stuff, one variable, or really it's two variable differentiation, is a rate of change with respect to x or rate of change with respect to y. Yep. That's the classic differentiation rules, and there are so many of them. And more with differentiation, as it gets more and more complicated, you have to learn rules. They're just rules you have to know to solve it. That's why later on in the course we do numerical methods for estimating derivatives and integrals. Then as we get to more complicated functions like a log function, the derivative of a log function, the natural log that is 1 over x. The derivative of log a of x is 1 over x a, natural log of a. And then we get the sine functions. So sine of x, so sine starts at 0 and goes up to 1 and down. The derivative of that is cos, because at 0 it's increasing. The derivative of cos means it's going up, while the derivative of cos is minus sine, because at 0 cos is at its highest and it's coming down, so it's minus sine. Derivative of tan x is sec x. There's a whole derivation of that you can look at. That's done by the quotient rule. And then more complicated functions like the inverse function of x. The derivative of that is 1 over square root 1 minus x squared and cos x. But all of these are in the log table book. They're all just different rules you have to learn or at least look up. In the rest of the video, I'm just going to do examples of the different more general rules. I'm going to do the basic rules, which is the multiplication or the power laws, the summation rule and the difference rule. Then I'll move to the product rule. Then I'll do a quotient rule. And we'll get into the chain rule as well. And also I'll look at some partial differentiation as well. So on to the examples. Our first example is a very basic function. Y of x is equal to x squared plus 5x cubed y sine x 11 cos x. So and note, you sometimes see it as written as just y of x or y or f of x, but really what it's saying is y is a function of x. So here we look at dy dx, the derivative of x, y with respect to x, or how does y change the function of x? So the derivative of x squared is just 2x. That's what I was once called the happy birdie law. The 2 comes down, and then you have 2 minus 1, which is power 1. Plus, I leave the 5 to the side because sometimes you do that. Then it's 5. Derivative of 3x of x squared is 3x. X cubed is 3x squared. Plus 9, once again, I don't deal with 9, I deal with the sine x. Derivative of sine x is just a rule. It's cos x plus 11 times minus sine x. So everything there is fine. I just clean it up slightly. So that's equal to 2x plus 15x squared plus 9 cos x minus 11 sine x. So in the tutorial, you'll get to see many examples of these kind of questions and have a blast of them to see how they go. Now we have the product rule. The product rule is based upon two functions multiplied by each other. So the simplest example of that is, or one example of that is equal to y of x is equal to x squared sine x. Okay? So in the product rule, you have two functions multiplied together. You have your x squared and you have your sine x. The product rule tells us to deal with them separately. You deal with the x squared, and then you deal with the sine x. So we call it u, and we call it v. So let's do the first one. U is equal to x squared. That's easily differentiated to give me du dx is equal to 2x. Straightforward enough. And now v is equal to sine x. So dv dx is just equal to cos x. Now, it's a product rule. And why it comes about is you don't want to differentiate all in one go. You want to take bit by bit and separate them. And to bring them together, you multiply the u by the dv dx and the v by the ux and add them together. So dy dx is equal to x squared cos x plus 2x sine x. Breaking it down to smaller parts and doing it in a very straightforward way means that you'll always be able to show your work, and if there is a mistake, it's a minor mistake and nothing to do with actually the implementation of the method. Our next rule is a quotient rule. The quotient rule is the same as the product rule, and actually you could just use the product rule to do it, but it deals with functions with our fractions. So if we take the simple example of yx is equal to x squared divided by cos x. In the previous one, we had it multiplied by, now we have it divided by, so it has to be addressed in this fashion. Once again, we have a u and a v. Yep. So let's deal first with the u. Very straightforward, just like before. U is equal to x squared. The u dx is equal to 2x. Yep. Now let's deal with the cos. V is equal to cos x. Dv dx is equal to minus sine x. Okay, now quotient rule is slightly more involved. It's not just multiply across, there's a minus sign involved as well. So how do we address this? What we have here is v times the u dx and then u times dv dx. So that's the same, except here we have a minus sign. So on the top of the line, y of x is equal to 2x times cos x minus x squared minus sine x. And all that is divided by the original cos squared x. Now, of course, we can do it, and I'll illustrate in class ways of doing this, but that's about it. So now you can just tidy it up. So that's equal to 2x cos x plus x squared sine x. I wouldn't clean it up anymore. You could try to do some division up, but that's where I would leave it. So our next rule is a chain rule. The chain rule is to deal with functions that are embedded in other functions. And this happens a lot. You have a function in a function in a function. So an example of this is y of x is equal to sine x squared plus 5x plus 1. Now, here what we have is something embedded in a larger function. Yeah? And so the chain rule has to take care of that. It has to deal with what's inside as well as what's outside. Once again, u here is equal to x squared plus 5x plus 1. But actually, I should call that u of x. The u dx is just equal to 2x plus 5. Now, we make a new function, v. Yeah, that's a function of u. So v of u is sine of u. So everything that we've now called u gets replaced. So now it's when we differentiate, we have dv du, which is equal to cos of u. So where we had an x, we now have just replaced it. But we weren't interested in dv du. We weren't interested in think. We're interested in dy dx. So we bring this all together. Dy dx is equal to du dx times dv du. Now here they cancel and we have dv dx, which is the original. But we don't do it like that. We actually put out the formula. So this is equal to, what's du dx? That's just 2x plus 5. What's dv du? dv du is cos of u. But we don't want the u's in there anymore. We want to get the original. So that's equal to 2x plus 5 cos bracket x squared plus 5x plus 1. And that's the chain rule. And so the chain rule can get bigger and bigger. There's a repeated chain rule you can have a look at as well. But really the same premise. It just keeps on getting either smaller, breaking it down to its smallest parts and then building it back up. And so that's the chain rule. The last kind of differentiation we'll deal with is partial differentiation, or the partial derivative. This is going to be the bedrock of a lot of stuff that we see later on. But it's actually identical. If you're comfortable with the previous rules, this is the same, except now we have x, y, and z. So if you have some function, which is a function of x and y, for example, and it can be written as 1 plus x squared plus y squared plus s squared y to the power 7, we can differentiate that in two ways. We can differentiate with respect to x, or we can differentiate with respect to y, because it's a function of both x and y. And that's where the partial derivative comes in. It's a partial derivative. It's not a full derivative of the function. Later on, when we deal with other types of float, you'll see how to address that. So, how do we deal with the different elements of this? Let's do an example. So, partial derivative, which is a fancy looking d with respect to x. So the derivative of a constant, which is 1 with respect to x, is 0. That's straightforward enough. The derivative of x squared with respect to x is 2x. Now we get to y squared. What is y squared? Well, y is a function of just y. So if you change x, will y change? No. So actually the derivative of that is 0. In this scenario, if you're only differentiating with respect to x, y is treated like a constant. So what do we do with the last one? We have x squared times yz. Well, part of you might jump and say this is the product rule. But it's not, because yz, once again, that's just a constant because it's not an x. So all we have is derivative of x squared, which is 2x, and the yz comes along. Okay. Let's do this again, but for y, df dy is equal to the derivative of 1 with respect to y is 0 because it's a constant, so that's the same. The derivative of x squared with respect to y. Once again, we're holding x constant and changing y. Will that impact x? No, so therefore it contributes nothing to the derivative of y. Y squared is 2y. And then the last part. Derivative of x squared plus y to the power of 7. Well, the x squared stays as it is. And we differentiate y to the power of 7 to be 7 y to the power of 6. And we can tie this up. I didn't do it with the other one, but that's 2y plus 7 x squared y to the power 6. And that is the rate of change of our original function with respect to y. And this is the rate of change of the original function with respect to x. And if there are 3 variables, so x, y, and z, we'd find the z derivative. And 4, we'd find the next derivative, and so forth. But the most important part of this rule is all the other rules fall into this. And all you have to remember is, if I'm differentiating with respect to x, I treat y like a constant. If I'm differentiating with respect to y, I treat x like a constant. And if you can keep that in your mind, then everything else is very straightforward and falls into place from there.